So today's speaker, welcome everyone to the monthly ECSS Symposium. This is where we get updates on some of the project work that ECSS folks are doing. Today we're fortunate enough to have Kathy Saint from SGI speaking with us. Kathy and collaborators, Celia DeLuca and a number of other folks are doing some really interesting work trying to couple a model that runs on a desktop, a hydrology code, with a high-end climate modeling code, CCSM or CESM now, I guess, that runs on Kraken, and looking at issues associated with that. This is it's been a really interesting model for Exceed. I think Kathy came to us probably well over a year ago via a simple help desk ticket that led to conversations with the security working group and a willingness on Nick's part to explore how we might possibly do something like this. It was unorthodox in a lot of ways, but there are a lot of scientific benefits to doing this, to running the codes this way. And is there a way that we can do this can this be a model for others who are trying to do the same thing? How can we do this safely? And I think Kathy has a very interesting talk prepared for us, and with that, I will let her get to it. Thank you, Kathy.
Hi, thank you, Nancy.
Presentation mode is now enabled. Presentation mode is now disabled.
Kathy, I was trying to mute the other participants, but I think you must have come in with a participant code for the phone line?
Yes, I did.
Okay. So if everyone else can just mute so we can hold down the noise.
Okay.
Thanks. Go ahead, Kathy.
All right. So as Nancy said, we worked on this project, basically coupling climate and hydrological models. So just the presentation here, I'll go through a quick description of the system, our objectives and motivation, the system design, and discuss some future directions. And then we'll run a quick demo. It's not a real flashy demo. If you saw me playing around with the screens earlier, it's a bunch of spewage coming out of terminals. But it's kind of interesting to see the data flow and how we ended up getting everything working together. So to get started, the primary objective of this project was to be able to couple a hydrological model and an atmospheric model in a loosely coupled distributed manner, taking advantage of some of the existing standards and frameworks such as ESMF and OpenMI. And I'll get into those in a bit. Our primary motivation for doing this work was to improve hydrological studies by using data from global and regional climate models when running the hydrological models. But there's a technology gap that exists between these types of models. The hydrological models typically run on Windows-based personal computers, while many of the climate models, as you all probably know, run on the high-performance supercomputers. Now, as I mentioned, I'll get into details of ESMF and OpenMI shortly, but by leveraging these technologies and frameworks, we were able to bridge this gap and get the models working together. This is a high-level description of the system. The hydrological model we're using is SWAT, and it runs on the personal computer, and you can see that up here. While the climate atmospheric model we're using, CESM CAM, runs on the high-performance computer, and we're using Kraken for this particular system. The communication mechanism we're using between the two models, what we've used to bridge them together, is called OpenMI. And so both of CAM and SWAT have been wrapped with an OpenMI interface, and that's all here on the personal computer. Let's see, in order to drive the system, up here, OpenMI comes with a configuration editor, and I'll go into that in a minute. But it's the driver of the system, gets things kicked off and running. Now, because all of the SWAT stuff is running on the personal computer and CAM's on the HPC system, we needed a mechanism to communicate across the network, and that's where ESMF comes into play. ESMF components, if you implement a climate model component as an ESMF component, we're able to then utilize these ESMF web services that are part of the ESMF library to help pass the data and command requests through the internet. So, and I'll go into all of these in detail. So first, we'll dig in. Okay, so first we've got SWAT. Now, SWAT is also known as Soil and Water Assessment Tool. It's our hydrological model. It's a river basin scale model developed to quantify the impact of land management practices in large, complex watersheds. Now, we chose SWAT because it is widely used in the hydrological community. It's open source, and there was a version of SWAT that had already been integrated with the OpenMI interface that was done by the UNESCO IHE folks. So that gave us a head start. We already had that part completed. The atmospheric part of the system, the climate model, we're using is CAM, which is the Community Atmospheric Model, and it's integrated as part of the Community I needed to change this, Community Earth System Model. It's CESM now. Now we chose CAM because it is also open source, and it already has ESMF integrated with CESM. So those components were already existing. And the ESMF team has a very close and ongoing working relationship with the CESM team. So that made that helped facilitate that effort. Now, ESMF provides an architecture and a software toolkit for implementing earth science models. Makes them easier to use, easier to interoperate, and supports component reuse among earth science applications. The basic idea of ESMF is to break up complicated applications into their logical components. So ESMF provides that framework and toolkit for defining and accessing a component, as well as the mechanism, the couplers, for communicating between the components. ESMF toolkits include software such as regridding software, calendar management, and other utilities in order to support modeling systems. And its primary data structures are array-based and multidimensional. Now, as I mentioned before, we've developed these web services that make it easy to support networked access to any ESMF component using standard web technologies. So basically, if you've got an ESMF component, you can access it over a network by wrapping it with the ESMF web services. Now, OpenMI, the Open Modeling Interface, it's an SDK, the software library that allow models to exchange data with each other on a time-step-by-time-step basis. Now, it runs primarily in a single-threaded environment on smaller, mostly Windows-based systems. It's very well known in the hydrological community. And a model is considered OpenMI compliant when it implements the I-linkable component interface. And its primary data structure for interfacing between models is the exchange item. And they're basically input and output exchange items that you define that you define for a model, and that specifies how data is exchanged. Hence the name. And then finally, we have the system driver, and it's what's used to control the process flow between the models. And since both models have an OpenMI implementation, we're able to use the OpenMI configuration editor to drive the system. As it's part of the OpenMI distribution. Basically, each model is defined by an XML file and the dynamic library that you create for that model for the wrapper, and that's loaded into the configuration editor. Then, using the configuration editor's graphical user interface, the input exchange items in the SWAT model are linked to the output exchange items in the CAM model, and vice versa for two-way coupling. That way, when the system is run, the SWAT model knows to get its input items from the CAM output items. And hopefully we'll see an example of that when we run the demo. Now, the configuration editor was convenient to use because we didn't have to do any special coding to get the models to communicate. As long as you have OpenMI compliant models, everything loads right into the configuration editor user interface. Okay, so now we can start getting into the details of how and where the system is implemented. From a hardware perspective, we used 4 different platforms for this. The personal computer is where the hydrological model, SWAT, and the OpenMI wrapper, the ESMF OpenMI wrapper, and the configuration editor are all contained. We have this running on a Windows server right now, but any Windows platform, like laptop, can actually run this. We have it on a server because it's in a central location, so we can all access it. On the HPC side of things, for this implementation, we split up the configuration onto 3 platforms within the Exceed environment. Kraken is the server for the atmospheric model. And the actual CAM executable, what we'll call the component service, runs on the compute nodes of Kraken. But in order to manage and communicate with this executable, we needed to go through the login nodes. And you'll see in a couple of slides, we'll have a couple of executables that run on the login nodes for this purpose. And then finally, because web servers don't typically run on HPC platforms, the Exceed folks set up a virtual Linux server for us to use as a gateway between the internet and the Kraken login nodes. So that's the hardware. When we get down into the software, it basically, well, the software on the client is the 3 parts, and we've kind of gone through this already, but we have the SWAT 2005 hydrological model, and it's wrapped with OpenMI. We have the CAM ESMF OpenMI wrapper, and this is what's used to communicate to the ESMF web services. And then we have the OpenMI configuration editor, which is used to link and drive the model run. Things get a bit more complicated on the server side. So first, the simple piece over here on the left is the web server. We're using Tomcat with Access, and we've implemented some SOAP services to communicate with the system. All communication goes through this web server. Now down at the compute nodes, this is where the component services, those are the executables that run the atmosphere on a CAM are run. Now, theoretically, each user will have their own instance of a component service since each run is specific to each user. But for this instance, we're only showing you one interface in this demo. And then finally, the login node. This is where all of this is controlled. The process controller, it's responsible for managing the component services. It starts them, monitors their usage, stops them if necessary, and it also provides access to them. So all communication to the component services from the client go through the process controller. Now, you'll notice the job scheduler box. This is basically just the batch scheduler that's provided on Kraken, and we've just wrapped that with some shell scripts. And finally, there's the registrar. Now, the registrar provides a repository of information about the component services. So when the process controller schedules a component service, it tells the registrar about it. When that component service actually starts up, it goes to the registrar and tells it the specifics about how to access it, such as its host name and its port number, since we don't know that information ahead of time. The process controller can then get this information from the registrar, and that's what it uses to communicate directly with the component service. Okay. So we start getting into see how the actual system flows. This is a collaboration diagram or sequence diagram to show the logical flow between the major software components of the system. There's basically 5 main steps in the flow: initialize, prepare, then there's the time stepping, which is the running, the finish, and dispose. So in the initialize phase, the driver initializes each of the models, and then the initialization of the of the CAM model involves essentially starting up a new session. And in this case, starting up a new session means scheduling a component service to start running. So this is where it communicates with the job scheduler. Once the component service is ready, the prepare step then gets the model set up for time stepping and exchanging data. In CAM, this involves executing the initialize routine, and there's an ESMF call to execute the initialize. Now moving on to the time stepping, the driver makes a request to the SWAT model to get values. Because of how the models are configured and linked in the OpenMI configuration editor, it knows to get those values from CAM. So the CAM wrapper then calls ESMF Web Services Interface, which runs a time step in CAM and fetches the data from the CAM output. And this phase repeats until we're at the end of the specified time period. And then finally, we move on to the finish and dispose phases, which are there to clean up the system. For the finalize call is made with the ESMF, and then in the dispose, we make an end client call. And basically what that does is it tells the component service that we're done, you can shut down, and the component service shuts itself down and exits. For two-way coupling, the system's pretty much the same, except in the get values section. When the get values call from SWAT to the CAM wrapper is executed, the CAM wrapper, again based on the configuration, recognizes it must first get a value from the SWAT model. So we get into a kind of chicken and egg thing. Which comes first? Who gets the data first? So with OpenMI, what you do is the first thing you do is you do an extrapolation. You come up with a number just to get things going. And so basically, SWAT goes to the atmospheric model, then the atmospheric model goes back to SWAT and says, first you give me data. And then SWAT extrapolates data, sets the value, and then the CAM wrapper can then go on and run the time step and do the run. And it does that extrapolation just on the first step. The rest of the time, it's actually making time steps within SWAT to get that value. And again, you just repeat this until there are no more time steps. So from a slightly different perspective, we'll move from the logical flow to the data flow. And this is how the data actually flows through the system with one-way coupling. Based upon the setup and the configuration editor, the linking of the SWAT input, which is the linking of the SWAT input exchange items with the CAM output exchange items. The SWAT implementation makes a request to get values from the CAM wrapper, which then requests via the ESMF Web Services to get the values from CAM. And then, as I mentioned in the previous diagram, for two-way coupling, CAM has to get data back from SWAT before it can get data from itself. So we have both input and output exchange items. And as I mentioned on the first time step, there's an extrapolation. For the rest of the time, SWAT makes the request to CAM, and CAM then goes to SWAT and says, let me have your data first. The CAM wrapper then passes that on to CAM and then runs the time step and then returns data back to SWAT. All right. Now I won't go into too much on this because we're basically just set up for a testing environment right now. We hope to configure this system for more scientifically relevant use cases in the near future, but we did want to point out the data variables that are being exchanged from CAM to SWAT. We've got these 5: air temperature, precipitation, wind speed, humidity, and solar radiation. And then from SWAT to CAM, we're passing evapotranspiration. Okay. Now a quick slide on we did a small scaling analysis to make sure there weren't going to be any roadblocks if we decided to increase either the size or the resolution of the models that we were using. So we did a scaling analysis, and you'll see there's 4 areas of increasing size, going from Upper Neuse watershed to the Neuse River Basin to the Carolinas and then the Southeast U.S. And then we ran CAM with 3 variations of resolution, 0.25, 0.5, and 1 degrees. And basically the main thing we got out of it was that CAM is pretty much always the gating factor in runtimes. It's what's taking up the most time of the system. There's that one exception, if you look down in the where SWAT for the Southeast U.S. actually takes a little longer than CAM at 1 degree resolution. But other than that, CAM's always the gating factor. And you'll also notice that the data transfer rates were actually fairly minimal because we're really not passing a whole lot of data across. As I mentioned in the previous slide, just 5 data points from CAM, or 5 data variables for each data point from CAM to SWAT, and then 1 data value from SWAT to CAM. Some future tasks. We are looking at configuring SWAT for larger scales, as the last slide showed, and also working with higher resolutions of CAM to try and make this more scientifically relevant. We're also in the currently working on replacing CAM with the WRF atmospheric model. The latest version of CESM actually has integrated WRF into CESM. And so because we've integrated with CESM, that kind of gets us a step closer to integrating with WRF. The main thing we have to do in that effort is create an ESMF component around the WRF atmospheric component. And then other stuff, looking to abstract the data, exchange information more so that it's a more generic kind of interface, and just little things like that. And that's pretty much the presentation. I wanted to get into the demo, but before I did that, were there any questions or anything? Comments?
Hey, Kathy, maybe some of this will come up in the demo, but I'd be interested in hearing at some point about how, what kind of concessions NICS had to make to allow this type of usage scenario, what kind of changes you had to make in your setup, how that communication's actually being done. And maybe that'll come up during the demo.
Yeah, I guess. Well, this slide actually shows the system. A couple of things we had to do. When I had this running originally, I had this running on my own Linux system in a smaller version of it, and so I had process controller, registrar, and all of the execution, the component services. Everything was running on one machine along with the web server. Some of the things when you get into these HPC systems, and I'm sure all of you are familiar with needing to separate processing on the compute nodes from access outside of Exceed and that sort of thing. And so separating the component service from the process controller was a big thing. Executing through the job scheduler, we knew we were going to need to do that. But the timing is a big issue for the process controller. Fortunately for this demo, we've reserved some nodes, so hopefully things will come back quickly. But when you kick off a job, you have to wait until the job scheduler decides it's ready to execute it. And in the previous system, that wasn't an issue. So we had to add in some stuff for monitoring, checking, waiting for the job to actually start. Now the Exceed folks were able to set up this the Linux server for us, and that was extremely helpful because without that we weren't able to access the login nodes from outside the internet. So that was another thing, that we had to separate the web services from the login nodes, and kind of that whole separation and encapsulation of the different parts was important for the system.
Is that Linux server, is that in your environment, Kathy, or is that at NICS?
That's I don't know if it's at NICS. It's within the Exceed system. That's what Suresh set up for us.
Oh, so that's probably a Quarry virtual machine at Indiana then.
Okay.
I would guess, yeah.
It's virtual to me. I don't know.
Yeah.
So that was set up by Suresh, and that was extremely helpful to get that going.
Great. Yeah, I see that he's on the call. So.
Okay.
Okay. Thanks.
Okay.
Hi, this is Amit Majumdar from SDSC. I had a quick question.
Sure.
So when whatever data is produced, and maybe in some of these climate or hydrology code, there could be a lot of data. What happens with that data, and how does the user get the data?
Well, the data that's being exchanged with the hydrological model, that's passed across the network.
I mean the output file, the final.
Yeah, the output files. We're not really addressing those. they get generated, and that's
the user would access to Kraken directly and do whatever the user does, right?
Right. That's kind of however you've done that before. But the idea here, now there are other tools I know for exporting output files to a gateway system so that you can then access them after a run. That's not really what we were attempting to address here, the problem we were addressing.
Okay, thank you.
Okay. Any other questions? Look at this. Okay. I needed to make sure all of my windows are awake here. I have terminal issues with PuTTY. Okay. So let me get back to the presentation. All right. I'm going to leave this in this mode. We'll be going back and forth now. Kind of, because there's not a whole lot as far as visualization for the demo, I kind of wanted to try and point out what was going on with each step of the demo, so you could see what pieces of the system were working. So let me go through these windows real quick with you and give you an outline of all the parts, and then we'll try and get things running. So this first thing here, it's called NICS. It's our Windows server, and this is where the configuration editor is run. This is also where the SWAT and the CAM wrappers are located. Those are basically just DLL files, software libraries that get loaded into the configuration editor when we start up. Then I have, okay, come on. What am I doing? I think I'm, there we go. Okay. Now I have 4 terminal windows here. The one in the top left, this is on that virtual Linux server. It's just a tail of the Tomcat log. And these terminal windows are just to give you an idea that data is actually moving around. These bottom 2 windows, the one on the left is the process controller. We're tailing the output from that. And the one on the right is the registrar. Both of these are running on the login nodes. And then the one on the this top right here is what I'll be using to look at the log files from the CESM CAM run. So right now, I'm just doing a stat to make sure there's nothing out there scheduled for me. All right. So, okay. When we go to the configuration editor and start things up, what you'll notice is it'll kind of sit there and hang for a little bit, because what's happening is that we're initializing the system. Now, the initialization, in addition to, well, the first thing it'll do when you load the model, it'll make this call to new client on the web server, which then goes to the process controller, and it tells the process controller, I need to create a new component service. The process controller goes to the job scheduler and basically submits a request for a new job. As I mentioned before, typically, the job scheduler takes its own time in setting things up and making sure the resources are there before it actually can run things. So there could be a wait period. For this demo, we've reserved some nodes, so hopefully the wait period is not long. Once the component service starts, it goes to the registrar and says, here I am, and I'm ready. And oh, by the way, here's the host that I'm running on, and here's the port number. This is how you can access me. And that's what the process controller ends up using. The status call is, while we're waiting for that to happen, while we're waiting for the component service to start, it's just doing a status, and the process controller gets its status from the registrar. And it just basically says, are you ready? Are you ready? Are you ready? And then when it is ready, the client, before it can run, still needs to initialize the model. And so this is where it goes through and it makes the call to initialize. And you see it goes through the web server, to the process controller, to the component service, and it makes a call to initialize. Now the component service updates its status with the registrar. So while it's initializing, it'll go to the registrar and say, I'm initializing. And then when it's done initializing, it'll say, I'm done initializing. And that's when the process controller can say, okay, we're done. And that's when the configuration editor can then get ready to run. So that's what hopefully we'll see now. Let me come to, okay. So this is the configuration editor. It's actually a fairly simple GUI. And the first step is opening up a predefined model configuration. It's not going to be real exciting right now because it's going to sit here and hang until it's ready to go. But I'll go ahead and open that up, and then hopefully, okay, we'll see. It just kicked off the job here, and so if I go here, and you can see it's running there. So if I do a QStat on this job, okay, it's queued up. And basically, all this is doing right now is saying get status. And like I said, it's not a very exciting demo. You just get to see a lot of spewage. And it's queued. I hang. We did reserve the machine, right?
Yes, I think. Yeah, we did. I'm going to check with our system in now.
Okay. It hasn't been taking too long. It's a fairly small job, so hopefully it'll start up soon. I've been testing it, so.
So what's your vision in general for how this would work, Kathy? Is this kind of an interactive experience from the desktop, or can it be done when results come in later, or are reservations always a key for this?
Yeah, I think when we're dealing with the HPC systems, unless you can reserve the nodes, you really have to deal with the wait time. And I would think, in a real world environment, instead of having the client sit there and constantly ping it, I would have a notification mechanism so that when it's ready, it would then go back to the client and say, okay, I'm ready. Whenever you're ready, let's get going. And kind of give it a time frame that says you got 15 minutes to reconnect and start using this or something like that. Make it smart so we're not utilizing resources when we're not not reserving resources that we're not using.
On the desktop side, are there interactive responses that are required once things start running on Kraken?
No, this is all done automatically through the configuration editor. It does the driving. And we even talked at one point about even replacing the configuration editor with a different workflow kind of tool so that you could use the automatic responses to do other stuff. The idea isn't necessarily human interaction. However, by having an interactive interface to a batch controlled system allows you to have that. Now, I know at one time, Nancy, you had actually brought up the concept of steering applications.
Yeah, because there are some systems in Exceed that allow you to make reservations, even user settable ones. It costs more in terms of CPU time, but still it can be done. And I could see the benefit for some applications. I mean, I think you guys were using this too, as there was a certain user community for SWAT who maybe wasn't as familiar with the high performance computing and CESM aspects, so they were able to get more detailed data for their desktop simulations. I think I remember Cecilia talking about that in a previous talk.
Yeah, Ricky, do you want to address that?
Yeah. So, one of the purposes here is to get to two-way coupling, because right now the primary way that we're doing coupling in these sorts of models is one-way coupling, where the climate model is essentially providing output that is then driving. So one of the things we're looking at a few years down is the ability for the hydrological model to also pass information back to the climate model to see if there are any regional interactions. So trying to get a little bit closer to the data without having to post-process it is perhaps our ultimate goal.
And I think that the setup with the virtual machine, does that now allow anybody with a desktop, or I mean, it's a specially configured version of SWAT for the desktop that has all of these hooks in. Is that right, Kathy?
Well, SWAT actually runs on the desktop. It's the OpenMI implementation. Basically, the UNESCO folks wrapped SWAT with the OpenMI interface so that we can control things via the configuration editor.
Okay.
And it allows you to define the data types for exchange. So you can specify that I need a particular I need temperature, and here's how we format temperature on our machine. And on CAM we've specified, well, we can get temperature as an output from our model, and here's how we format it. And then the configuration editor and the OpenMI interface handles the exchange of that information.
So you would initially envision it being used by a small research group who all has this particular configuration of OpenMI, and then also SWAT installed, and then use the CESM installation on Kraken?
Yeah, I think it would be used by these hydrological scientists who need the information, but don't necessarily have access to all of the high performance systems.
So this is Ricky Root again. So one of our big goals here is that, say, within the SWAT community, one, they are operating within a framework, and what we're seeing here is rather than perhaps scaling across Silicon, we can scale across research groups and scale across an entire community. So on one hand, one of our real goals is to engage more minds that might be interested in this problem. The second thing is, SWAT is just one example of a hydrological model, and also just one example of the types of desktop models that are being used in climate. Increasingly, they're localized, regional, integrative assessment models and the like. So we're also seeing this as possibly opening up other classes of models that are widely distributed within the research and also the practitioners' environments. So we're looking at this as coupling communities as much as we are as coupling computers.
Yeah, it's interesting because it really is very much we call them science gateways in this project. It's very much a model like that, but it's so different in this communication model rather than, say, a web interface where people log in and run the simulation.
Mm-hmm.
Yeah, very interesting approach, and I'm happy that our security folks were willing to take the first steps to at least consider how this might work, because I think at other sites folks were not. So that's how we ended up working with Kathy and Hai-Hong at NIC.
Yeah, so I'll make a comment about the security, which is, one, thank you for your help. I used to manage the High Performance Computing Center at NASA Goddard, and I will say that all of our projects that sort of were innovatively trying to connect with outside communities and the like ultimately did not happen because of security. So this is actually quite a significant achievement, I think.
Yeah, thank you, Ricky. It looks like Kathy's job is starting to run.
Yes, it is.
Yeah, I think we reserve the nodes using another account, and Casey, you use the one account which is not.
Probably the old account number we had.
Right.
Yeah.
Right.
Okay.
Yeah. So,
well, it's running now.
Okay. Yeah.
So good. If you'll look real quick, thank you, Haihung.
No problem.
Over on the right is the registrar, and you can see once it started, it notified the registrar that it's initializing, and then when it completed, which it's completed, it told it it's done, and all that information all got passed through the process controller and the web server here, or the web server. So okay, there it is. As exciting as this is the configuration editor, and basically each of these yellow boxes represents a model, and this is the KDS are just my initials. That's how I uniquely identify stuff for me. And then this is the instance of the CAM model. Down here is the instance of the SWAT model, and for the life of me, I can't figure out why I can't get it to print out on the screen SWAT. But that's what it is down here. And then this blue box is what they call a trigger in OpenMI, and that basically is just what kicks things off. So if you look at, say, the model properties, these are all of the input and output exchange items that are defined within that wrapper. So SWAT has a whole lot of input and output stuff. When we did the wrapper for the CAM, we just defined these 5 that I mentioned before. And all of that's defined in the wrapper code. Now here's the link. These blue arrows indicate a link between 2 components, 2 models. And that's what we have down here is we've defined the links between output exchange items in CAM to input exchange items in SWAT. And that's what these things are all down here. And that's basically all you have to do to link up a couple of models to load them in. Once you've implemented them as an OpenMI interface. That's the hard part. So we'll go through this quickly now. That the next step is to run it, and so when things run, you'll be spewage everywhere. So I'll go through the flow real quick. There's basically 2 parts to the run, and basically when I say run, we're doing a time step. The configuration editor, based upon this linkage, you'll notice trigger goes to the SWAT model, which then goes to the CAM model. So in the configuration editor, it goes to the SWAT model and says, get values. The SWAT model says, I need to get that from CAM, so it goes to CAM and says, get values. What that means to the actual CAM implementation is first we need to run a time step. And so through the web services, to the process controller, it makes a request to the component service to do a run time step. And as you can see, it updates the registrar. I'm running a time step. When it does complete running a time step, it sets this output data into a location that we can then fetch from later. And it tells the registrar, okay, I'm done. And then the second step is to actually get the data. And that's what this is right here. There's kind of 2 parts to getting the data. The first thing you have to do is get the data description so that we know what data variables we're retrieving and the size of the data coming back. And you only have to do that once because it's assumed that's the same for every time step. And then you actually make a call to get the data. And then the CAM wrapper returns all of that to SWAT, the data. So we'll come back here, and within the configuration editor, you just make a call to run, and you say run. And basically what you'll see here in the client is it's going through these time steps, and this is the time frame that we're using. Now if I come back to my terminals, I have to wake up the windows. Hopefully they're still going. There we go. This is just the terminal delay. You can see all the data actually spewing across there. There we go. Over on the top right is the actual CAM execute, and you'll notice a lot of output information in there. That's just, like I say, spewage, and it just crashed on me. I was afraid of that. It's taken too long, I guess. But that's basically what happens is that it executes. I don't think we want to get it restarted again. It goes through all of those different components, fetches the data back, and returns it back to the SWAT model. Like I say, there's not a whole lot of visualization with this. It's just a matter of exchanging data back and forth. The final step, which we won't see, is the finalize, which when it's done running on the configuration editor, it makes a call to finalize the system, and that again through the web services, the process controller goes to the component service and says finalize, and then from the CAM wrapper, after doing a finalize, it then says, okay, we're done with the session, let's end the client, and it goes through the system and tells the component service, go ahead and exit your service loop, and that's basically what's been keeping it running. And so it says, I'm done with the loop, let's go ahead and exit the application, and it tells the registrar I'm completed, and it shuts itself down. So that's basically it. Any questions or comments? No?
So at the end, the user has a completed SWAT run that's been fed input from CESM along the way?
Right, exactly.
Right. Okay.
Yeah.
Yeah, very interesting. And so as far as you're concerned from the exceed perspective, do you sort of have what you need to scale up? I mean, I think I could think of one next step, which would be probably running this. I don't know. It might get kind of complicated. Running this as a community account rather than under your username, Kathy, and having other people able to do this, and then keeping track of accounting.
Yeah, exactly. That was kind of like a whole other problem I wasn't really looking to solve. I know that's been solved for other people.
Right.
But yeah, that's if we were to set this up as a real world application, you'd want to set it up either as like you say, a community account, or set it up so that you can, because you want to keep track of everyone's usage of the system, right? So.
Right. I mean, in a way, you could at least start with named individuals as a stepping stone.
Right, and use the gateway to handle all of that.
Yeah.
But yeah, the exceed, being able to do this within this platform was, as Ricky mentioned, being able to get to work with the security folks and allow us to set up, ports on these servers and access them through the software has been incredibly helpful, and shows that you can make these batch applications interactive and still be responsible applications.
Yeah, that's great. I'll definitely pass along those comments. The security folks don't often get to hear that sort of thing, and none of them are on the call, I see. So.
Well, yeah, and Suresh and his team has been very helpful. We had a system go down on us for a little while, and they got that up right away for us. And so Hai Hang and everyone has been very helpful in getting this system working. So we really appreciate all that.
Great, glad to hear it. So are there any more hurdles from the Exceed point of view for you, or now that you have this Linux server, are you kind of off and running?
Yeah, as long as this existing system exists, this setup exists, I think we're at a point, like you say, I think the whole account information, that sort of thing, we could probably use as far as using other people's examples as how they did it, to maybe make that more accessible to other people. I don't know that we're past the prototyping stage for this yet, but other than that, I think the Exceed system is where we need it to be.
That's good to hear, because I know it's been a long time coming. I know we've kind of tried this for in fits and starts for quite a while, and it's great that it's finally got enough momentum to take it to where you need to be.
Yeah, I couldn't be more pleased with it.
Excellent. Any other folks? I'm monopolizing the conversation here. Any other folks on the call have questions for Kathy? Definitely kind of a non-standard type of Exceed application. Well, great. With that, I want to thank Kathy for taking the time to present, Ricky for joining us, Hai Hong for all his hard work, Suresh on the project, and we'll talk to you all next month for the next ECSS Symposium. Thank you very much, everyone.
Thanks, Nancy.